segments after our tests?
Yes. The segments run from the bottom of the hour to 20 after the hour. So you go from, 5:30 to 6:20. Okay, so that'll be your test. And hopefully everybody will be finished in 50 minutes. Some people take like 20, some people take the whole 50 minutes, okay? But then everybody takes a break, and then come back at 6:30 if you want. I will take attendance. We'll probably have a test or a quiz at the end of the night, but okay. So there's 3 segments. So the next segment will begin at 6:30 to 7:20, 7:30 to 8:20. Yeah. Any other questions? Okay. Alrighty. As far as I could tell, this is where we need to pick up, because I put the word Thursday on this slide. I think that's pretty safe. So, what temperature do you guys set your thermostat at when it's winter?
72.
72? 68? 67? Kind of a nice assortment. Well, the deal with this thing is whether it's summer or winter, you set it at 65. So I don't know. I have mixed feelings about that. It seems a little chilly actually in the summertime. 65. It seems a little chilly in the summertime and the wintertime. But anyway, what you do for a given location is you see how far away you are from that temperature of 65, and that's how hard either your furnace has to work in the wintertime or your AC needs to work in the summertime. And then you add up those, degrees, you sum them up, and you say that is the number of cooling degree days or heating degree days. Okay? So, and we're going to see, not so surprising, who do you think has the most heating degree days? Probably near the equator-ish. Or sorry, that'd be cooling degree days. Who has the most heating degree days? Near the poles? Yeah. And the equator has the most cooling degree days. So just to kind of highlight a few, heating degree days, Anchorage, Minnesota, I know, I do. Okay. For those same locations, if we go ahead and look at the summertime, how often they need to use their AC, it changes a little bit. Okay, not so surprising. These annual annual amount you need to run your furnace and annual amount you need to run your AC, okay, those translate to pitching if you're paying your own electric bill. So there's a couple of maps that kind of summarize them. Oh, it says skip the next 2 slides. Actually, here they are. Heating degree days, cooling degree days. Okay. So the last topic is we talked about temperature, and temperature is all well and good, but if you're doing your weather log, they do the temperature, dun, 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 and then usually they have a feels like temperature. And the feels like temperature is either a wind chill temperature or heat index temperature. That's the feels like temperature. Okay, so if it's windy outside or cold outside, basically what they do, and there's a chart I'm going to show you, that they take what the thermometer's reading, and they look on the chart with what the wind is blowing, and they come up with what it feels like if you are a warm-blooded creature. Okay, I say warm-blooded. Inanimate objects don't know wind chill temperature. They're like, I don't care. Okay, it's only that the folks that are counting on basically a little layer of thermal energy to kind of, when you're walking around, you have an aura of thermal energy. Okay, if the wind comes and it takes your aura away, so it makes you feel colder than you really are. Okay. So let's see. I'm going to click on this. I can't remember what that link does for us. Well, let's go to National Weather Service site, weather.gov, and let's see what their feels like temperature is now. It's supposed to get warmer, right? It's cold right now. Maybe. I guess I didn't click on it. So doing your weather log, you must be able to find your data okay and everything. So this is just one site. So 52632. Do you think it's ironic that, like, Groundhog's Day, wasn't it Groundhog's Day that, like, school was canceled because of weather? I just think that's ironic. Okay.
It was great. It's my 4-hour photography class.
Oh, dang.
Yeah.
That's no fun. You're taking photography too? Yeah.
It's awful.
The photography's
4 hours.
awful?
Well, it's not. The class isn't awful. It's just
4 hours is a lot.
4 hours, and she drags it. She drags it out. It's awful. She's using all 4 of those hours.
Good for her. Sorry. Oh, okay. No comment. So you were glad it was canceled is the point?
Oh, yes.
Okay. Groundhog's Day, did you guys catch the...
Saw a shadow.
He did see a shadow, you know, so... But don't you think it's backwards? So the sun was out. Okay, sun is shining. He sees a shadow. He runs back in. Sun's out. There's 6 more weeks of winter. You're like, dude, is that not backwards? I think if he runs back in, because the sun's out, that spring should just be around the corner. I'm just saying.
You should be a philosopher.
But somebody told me that the stats on probably Puxatawny Phil, the groundhog, he runs about 40%. So along my lines, is if he just reversed his thing, he'd be running 60% accurate. That's easy. But okay, let's look for the feels like temperature. Okay, so -9 degrees Celsius. Let's stick with the 16 Fahrenheit. Much better, right? 16 degrees Fahrenheit. And they said that, and let's go ahead and jot these down. Okay, so they said that the temperature, I'll put T is equal to 16 degrees Fahrenheit. I'll go ahead and put the Celsius temperature in case that's that's what the table's in, I can't remember. And we'll also need the wind. They said the wind speed is 6 miles per hour, which is not bad. And they said that the feels like temperature, the wind chill, they said is 7 degrees Fahrenheit, and that's -14 degrees Celsius. Okay? So here is the table I was talking about. Let's see if we can find this on the table. All right. So you can see that the feels like, or the thermometer temperature's along the top. So we need to find, and it's in Fahrenheit, that's cool. So find 16. I see 15, so that'll have to do. That's okay. Okay, and then what you do is you find the wind speed of 6, which I got 5. Okay, and so there you go. That's how they got 7, where they intersect. Okay, so warm-blooded animals basically have that going against them. But notice that at a temperature of 15, if you jack up the wind to 20, which could happen around here, you're looking at -2 Fahrenheit, even though your thermometer says 15. So your car radiator in your car feels the 15, but you, because the wind basically whips your little thermal energy blanket away, feel like it's -2. Okay, so that's how that works. So the other feels like temperature happens in the summertime for us. I'll just go ahead and put all this up here. And it has to do with humidity. So we definitely, and it's called heat index. So we don't have a feels like heat index right now. Okay. But when it's muggy, we're going to be talking about water in the atmosphere. When it's high humidity, okay, it feels like you can't breathe, right? But the other thing when it's really muggy is that your sweat can't evaporate. Why doesn't that liquid want to evaporate? Because there's already all sorts of gas, water particles in the air, okay? So since it doesn't evaporate, basically it shuts down your evaporative cooling. I don't know if you remember, but I told you guys to write, maybe I said evaporative cooling when I said one of the reasons that large bodies of water have a moderating effect on locations that live on the coast. Okay, because what evaporation actually gives a cooling effect. So there you go, in a nutshell. So this is the table we would use in the summertime. Okay. Yeah. Actually, in Chapter 4, which we're going to get to here tonight, I know Chapter 4 is in the next unit, but we're done with this unit, right? Okay. In Chapter 4, we're going to talk about how you calculate, or how, I'm going to bring in some devices. I've got them in the lab. They're fancy, not really. But they're like little 2 thermometers. One has a little piece of fabric over it and one doesn't. That will allow you anywhere, anytime to knock out what is the humidity in the air. So, all right. Part of the reason I left these few slides till tonight is so that you didn't have to do 2 chapters, just 1 chapter. Okay, so Chapter 3 will be due next time we meet. By midnight. So, any questions about all that? Okay. Now on to, it's not completely different. So this is stuff that will be on your next unit exam. Okay? So I feel like we should all get up and stretch or something.
Do you have an extra of those PowerPoints printed off?
No, I don't. Sorry.
It's all good.
But they're available, but I don't have an extra one. So one of the things we're finally going to get to talk about is this idea of cloud formation. See the clouds up there? Okay, fog. What do those both have in common? What do you think?
Moisture.
Moisture, exactly. Moisture, the milky white, did I ever tell you kind of what phase water is in if it's milky white? What phase is it in? It's not a gas, it's not a vapor. Gas and vapor are the same thing. So it's a liquid or solid. Yeah, exactly. That actually fog is water. Little L means liquid. Exactly. Oops. Usually put it in parentheses. Exactly. And you know one of the reasons it appears milky white? Okay. Because in its liquid state, actually, light, visible light from the sun, gets all kind of scattered and kind of confused. Okay? And it makes it opaque. It's multiple scattering. It comes back at you. Yep. So do you think that there is gaseous water down here? Water vapor? I do too. Water vapor all around. But where it's milky white, that's liquid.
What kind of cloud is that?
It looks like a cumulus cloud. It's kind of a catch-all. Cumulus just means fluffy. But there's a cumulonimbus, which means it's
Those are
fluffy
the big
and
nasty
rain.
ones.
They are. Yeah, and then those are the 2.
The ones are in the background there, the long flat ones.
The long flat ones are probably stratus. We call those stratus. These are cumulo. And if they're just in the middle layer, there's regular stratus. If they're, if they're lower, they're regular stratus. If they're middle, they're altostratus. If they're upper, they're cirrostratus. So, the water cycle, hydrological cycle. You guys are probably really familiar with it. Look at all the snow out there, right? Okay. Basically, we've got a couple of ways to get water into the atmosphere from the geosphere. That would be evaporation, and plants do it. They open their cute little stoma. That's about the only plant word I know. And they push out water, okay? So then, as you know, we have different ways that it goes from the atmosphere to the geosphere. Okay, so we have atmosphere, geosphere, biosphere. What's the other sphere?
Stratosphere.
No.
Atmosphere.
I said atmosphere, geosphere, biosphere. No, these are like the different interacting. Those are like the layers of the atmosphere.
Atmosphere, geosphere, biosphere, and hydrosphere.
Hydrosphere. Is that what you told me before?
No.
Okay. Hydrosphere is right.
Second.
Second best.
Hydrosphere. Yes, and actually that's on your test.
Cool.
Okay,
Writing
I
that
know,
down.
because I just recently made it. And on your review sheet, that falls under Chapter 1, where it says various Earth's spheres. So that's what I'm talking about. That's what I'm talking about. So we have different ways of water going back and forth. So the whole kind of fourth, where basically goes from the atmosphere to the geosphere to the Earth, would be precipitation. In general, precipitation by definition means it basically falls to the Earth. So fog is not precipitation, and dew is not precipitation. Frost is not precipitation, but snow is. Okay. Then, actually, within the geosphere, we have a little bit of movement. So this is talking about the hydrological cycle. Okay, you see the evaporation, the transpiration, okay, and then you see the precipitation. So one of the things we are worried about as the temperature of the Earth generally gets warmer is kind of changing this balance a little bit. All right. So, in order to talk about clouds, in order to talk about water becoming a liquid, okay, we need to understand the whole liquid, gas, and solid thing. So, up here you have liquid, gas, and solid. And I could animate this, but I'll just kind of show you what the animation would look like on here. All matter is in motion. At what temperature does all motion stop? Absolute zero. It's on your test. Okay? See, you'll do fine. Yeah, I think that's under chapter 3. Okay, so all matter has motion, so that's at absolute zero. So here's the deal. Gases have, I think I might have mentioned this before, gases have the most amount of motion. Did I say this before? So I'll kind of show their motion with a big long arrow. Okay, liquids have a moderate amount of motion, shorter arrow, and these cute little solid molecules are just wiggling. Okay, so the length of the arrow is showing their motion. I can't remember, did kinetic energy make it to your, I'm second guessing, I thought about it, but I don't think it did. But if something has motion, then you can go ahead and say it has a certain amount of kinetic energy. Okay. So all matter has motion. All right. So we're not all about just matter in general, but when we talk about the hydrological cycle, we're working with water, right? So these cute little Mickey Mouse molecules are water, H2O. You see the central oxygen is red, and you see the two little white, makes it Mickey Mouse, hydrogen atoms. So here is water when it's a solid, okay, and here is water when it's a liquid. And I can make motion here. I can make a little vibrational motion here, and I can make more sloshing motion over here. This is snow, this is liquid water. Okay. So among things that you might see, do you see the dots? Which one has more of these dots?
Solid.
Solid has more of those dots. And actually, those dots are, they are what we call, I don't mean to get, can't remember if I use this term or not. We call those intermolecular bonds. And like it says, there's a special type of intermolecular bond called a hydrogen bond, but I'm not too worried about that. Here's the deal. If you get ice, if you take ice and you heat it up, what does it do? It melts, exactly. Okay, so this is basically showing you the melting, and that heat, what that heat is doing, I just think it's so exciting. What that heat is doing is basically breaking. We can't see it. We could if we had the right instrument, probably. I don't know. But what that heat is doing when you melt ice is it's breaking some of those intermolecular bonds. What would happen if we heat liquid water?
Evaporate.
It goes over here to a gas. Basically no intermolecular bonds. Exactly. You break all of those bonds. So that actually, if you kind of keep that concept in the back of your mind, that will help. Okay? It takes energy to break those bonds. I think this one will play for us. The latent heat of melting is the amount of energy you got to pump in to go ahead and get something, an ice cube, to liquefy. Latent heat of melting. Okay, the latent heat of freezing is the amount of energy you get back when the liquid solidifies. Okay, latent heat. So the two things you add energy to in order to get them to happen, the two phase changes, would be the solid to liquid and liquid to gas. You've got to add energy. You do. Okay, the latent heat of melting and the latent heat of evaporation. I'm going to put numbers with those here in a minute. Okay, going the other direction, okay, going from a gas to a liquid or a liquid to a solid, those cute little dots, those intermolecular bonds are being formed. Whenever bonds are formed, whether it's that sort of bond or a chemical bond, energy is released. Okay? And so actually that is another type of latent heat. It's all latent heat. Okay? Just latent heat of different things. All right. So latent heat. The next slide goes ahead and puts some numbers with those. So I put this slide together to kind of show what we've been talking about the solid, liquid, and gas. I'm hoping that we're all going to kind of get on the same page. Anytime you see vapor, I want you to think gas. And unfortunately, I kind of go back and forth between those two terms. Water vapor, water gas, it's the same thing. But if you're going from left to right like this, guess what? You got to add energy. And that's the thing we're all kind of used to. We're used to whole melting and evaporation. Okay? I'm going to, let's see, here or maybe later. Maybe I'll do it right here. Can you think of a case when something goes from a solid straight to a gas? I bet you, are you thinking of, you shouldn't play around with it, but have you ever gotten that solid CO2 from, I don't know if High Feet still sells it, but dry ice? Okay.
Liquid nitrogen?
Liquid nitrogen goes from that goes from a liquid to a gas.
Yeah.
But it does it right handily.
Yeah, very quickly.
Yes. But something going from a solid to a vapor. Yeah. And dry ice is a good example. Okay. And what that does is, what they have to make that CO2, that chunk of solid CO2, they basically took CO2, which is a gas normally, under normal pressures and temperatures, and cooled it down and pressurized it and made it into a solid for us. Okay. Let's see. CO2. It makes things cold, right? Or the dry ice makes things cold. Check this out. Do you think a lot of bonds are broken when it goes from a solid to a gas? Yes. So in order to break bond, energy had to be put in. Guess what? If you're holding it, it's getting the energy from your hand. I'm just saying. It gets energy from wherever it can. Usually, hopefully, it just gets energy from your cooler, so it cools down your cooler. Okay? It's a good thing. I would argue that sometimes we call that sublimation. I would argue that sometimes we have sublimation with a pile of snow. Okay? It goes something like this. Okay? Let's say you have a pile of snow, and it just takes forever, and you never get any more snow, but eventually that pile of snow goes away. It never gets warmer gets above the freezing point temperature, so it's always colder than freezing. I would argue that some of that solid goes straight from a solid to a vapor. That's my story, and I'm sticking to it. But another example, you guys don't have these like stupid little ice trays that we used to have before we had ice makers? You have ice trays? Aw, good for you. You have ice trays too? Well, do you ever go and is the water all gone because you left them in there too long or whatever? The ice tray in there?
I don't know. Usually we don't have ice for that long. We use it pretty fast.
You freeze it and use it.
Yeah.
Yeah. How about you? Have you ever gone back and?
I haven't really paid attention.
I guess I could try. Don't use this ice tray.
Yeah. Yeah, because over time, basically, it will go straight from a solid to a vapor in your. And then, you know what? What we say deposits on your meat. So maybe don't do that.
Oh.
But it can give it the meat freezer burn and stuff too.
Yeah.
So you kind of have that sublimation, and deposition is the whole vapor to a solid. Yep. All right. So going backwards, and you kind of have to, this is flipped around to what I said, the solid, liquid, gas, and now it's gas, liquid, solid. But basically now from left to right, bonds are being formed and energy is being released. And I'm going to highlight this one right here. The latent heat of condensation. You're going to see that later. Okay? The latent heat of condensation. So condensing. That's the whole vapor going to a liquid, right? That is a player. The Milky White we talked about, the whole fog or the Milky White cloud, basically in the vicinity of that condensation from a gas to a liquid, it is warming up. Okay. Those thunderstorm clouds, what makes those thunderstorm cumulonimbus clouds so just crazy is basically they have a lot of condensation going on. They are very hot. That heat makes them unstable. In a nutshell. Okay, so here's the figure from your textbook. I like this one because isn't that just adorable? Like the polar bear standing on solid ice, floating on liquid ice, water vapor all around. But anyway, so we have solid, liquid, gas, kind of going back and forth. So we would call this the latent heat of melting. And for some reason in physical science we call it fusion. Latent heat of fusion or melting is calories seems like an energy unit. So 80 calories of energy is what you got to pump into, I guess that's per gram to get it to melt. Okay. If you take 1 gram of liquid water and you freeze it, it's going to release 80 calories. So not so surprising. Those are latent heats. Latent heat of evaporation and latent heat of condensation is 800 units of energy or calories of energy released, absorbed, absorbed, 800, 600, my bad, 600. That's 600. Okay, 600 of calories of energy needs to be sucked in to go ahead and get it to evaporate. And during condensation, 600 calories of energy are released as it condenses. So we talked about the whole sublimation. Basically add 600 plus 80, you get 680. And I use the word deposition for what happens for your in your freezer burn. Okay, so basically water vapor is condensing on your pizza that you have in there for, I'm not saying we have, but like a year or something like that. Frozen beef. So definitely we have energy moving around. So Milky White liquid, Milky White solid. Let's go ahead and take a break here. Everybody get up and stretch your legs. And we'll come back so I can get some things ready. About 15 minutes or so. Nice long break. I don't know if it's long enough to go get you something to eat.